Thanks, Simon. Yeah, so I've assumed you've done all the hard work and found the set of studies that you are going to want to meta-analyze. And so I'll go over a review of methods and also try to connect it to traditional methods. So if you have ever conducted a meta-analysis in biomedical studies at all, then you might know some methods, and I'll try to connect those methods to what we do in meta-analysis and review the major approaches that we use, and then talk about some limitations and things you might want to worry about. Okay, so this is what I would say if I went to a textbook on meta-analyses, just traditional biomedical meta-analyses, and said, what are the steps that we need to do? And a lot of these have just been covered by Felix in terms of specifying what you set out to do, specify what are the eligibility criteria, and what's going to be the pool of studies you're going to draw from, what are the ones that you're going to exclude. But then we have these things: collect and validate the data rigorously. Well, this amounts to, usually in a traditional setting, finding the estimates and standard errors and making sure there's no typographical problems. And that's something we can do, and we do worry about. We can actually make plots of all the points and make sure they're, for example, in the brain. It's a good thing to check. But the thing we cannot do is, because this is just a fundamental limitation of neuroimaging statistical analyses, we don't get standard errors on the locations of these coordinates. That just doesn't come through. That's not part of the information. So that's something that's very important in a traditional meta-analysis that we cannot do, and so there's no measures of precisions. We have certainly the sample size, and we pay attention to that, but that's one thing we can't do in a imaging meta-analysis. So then we compute the average effect. That's basically like our meta-analysis map, and I'll talk about different ways we can create that. And then usually they'll say in a traditional setting you should look for publication bias and conduct sensitivity analyses. So publication bias is something I'm interested in, I'm working on, but we don't really have any standard tools. And Felix mentioned a little bit about sensitivity analysis, which is not easy to do, but basically amounts to just changing the set of studies that you're conducting, that you're using, and see how your results change. So let's see what we can do in, what we do in standard meta-analysis. So if we actually had the data, if we just had the images, or if we just had a meta-analysis study that you wanted to conduct on traditional non-imaging measures, here's the menu of things that are available for you. Some of them are based solely on the p-value, or equivalently the z-value. You may have heard of Fisher's statistics. That basically just amounts to averaging the minus log p-values, or Stauffer's, which is just amounts to averaging the z-values and getting the details right. But if you look in the traditional meta-analysis literature, these are regarded as last resort. You shouldn't just be using these because they're not accounting for within the individual study variances. And so they recommend instead doing at least a fixed effects approach, and there you need the estimates and the standard errors from each study. And this is advantageous because this gives a balance for each study according to its standard errors. But as a fixed effects model, it doesn't account for the between study variation, and so the best practice method in non-imaging meta-analysis is a random effects model. So usually when we think about random effects in a group analysis, we want to be sure to account for the subject-to-subject variability. And now our concern is the study-to-study variability in the response, and this could reflect differences in the way the study was conducted, fundamental differences in the population that was studied, but that generally, if we can, we would like to account for these kind of possible random differences. And they use the term meta-aggression when you can do one thing further, which is to account for different effects that might explain differences between the studies, whether these might be sort of just fundamental differences in the type of stimuli used, or maybe even looking at sort of publication year to see did anything change with time. These are the tools that are available to the non-imaging meta-analysis tool community. And so let's see what we can do in the imaging meta-analysis. So the first thing you might say is like, well, we are getting quantitative responses at each point in the brain. Why can't we come up with a quantitative response that we can use and collect across papers and use that in a meta-analysis? And the point is that it's actually almost impossible to do unless you're working in an area which relies extensively on regions of interest, where they average the response in the region of interest, and that region of interest has been constructed in a non-circular way. you really can't, you don't have anything to meta-analyze because those measures are going to be biased. And one way to see why that is imagine here, I just draw a picture of going through the brain. If there was a big sort of effect in the, across the front of the brain here, and this red line represents a true bold effect if I could scan everyone in the country, in the entire population. But of course, we don't get all that data. We get a random sample of it, and there's going to be some difference between that. Well, sometimes it's going to be below the true, and sometimes it's going to be above. And what do we normally report in papers? We report the peak. So the peak is always going to be a biased estimate of the true percent bold change in any given study. And so this is why we cannot do and use traditional non-imaging meta-analysis methods, because all of the quantities, all the percent bold changes that are reported typically are biased measures, and they're going to be overly optimistic measures of the bold change, and you don't want to trust those and feed them into a traditional meta-analysis, non-imaging meta-analysis. So what do we have at our disposal? Well, we have these two different broad classes, and Felix has already mentioned them. I'll just go through them again. What we refer to as intensity-based meta-analysis. So that is this case where you actually have the full image data at your disposal from each study. Now, again, this is not very common. So what could we do? Well, we could combine the TEP images. That's if you had them, you could use one of Fisher's or Stauffer's methods, but again, that's not the recommended method. If you had the contrast of parameter estimates, the contrast images, you could also do that. That would be good. You could just analyze those in a regression analysis, but of course that's not good because you're not accounting for the different study size that created that contrast. So something that it would be better would be to use both the contrasts of parameter estimates and their variances. And FSL does this actually very, very nicely, but it does incorporate both the estimates and the standard errors when you're combining a bunch of subjects into a group. And it turns out that same kind of framework can combine groups of COPEs and VAR-COPEs from different studies into a meta-analysis. And that's something that Camille, my postdoc, has been working on looking at. But all these things depend on the images being shared, and that is not really done right now. So this is kind of a non-issue, though I'll be happy to talk more about this. That's something I'm excited about methodologically, but there's just not enough data around to do much with this. So we're left with coordinate-based meta-analysis, and here are the kind of three prominent methods that have been proposed. The first one we've heard a bit about is activation likelihood estimation, and another related method, multi-level kernel density analysis, and a third sign difference mapping. And I'll focus on these first two since those are the two that you see the most of. So all of these methods are kernel-based methods. So we're trying to get from this awkward situation where we want to make maps. We want to make images of the activation if we had only had that original data. But all we have are these coordinates. So the kernel is the bridge that takes us from the XYZ locations that are reported in the paper to a map, some sort of map that we can start to analyze in our traditional methods. So it starts by placing at each point where there's a foci reported a kernel, and putting a copy of this kernel. This could be either sort of a hard sphere, like a disk kernel, or a Gaussian kernel. This is a prominent difference between the two methods I'll talk about. But you, in the end, get an image that is a representation of the information that's contained in all the study's foci. And it's a map. And then once we have one of these maps, one per study, we can start analyzing them in not exactly the same way, but in ways that are analogous to how we analyze our brain image data. One of the key problems is that this, as you can maybe see from here, this kind of data is highly non-normal. It doesn't behave like the continuous data that we actually collect, and so you have to use alternate methods. And so most of the methods that are used use some sort of Monte Carlo test, where we say under the null hypothesis there should be no spatial consistency across subjects, and so we randomly move around the foci, and I'll get to the details of that, and then recreate our map, our meta-analysis map, and then we compare how our actual observed map compared to these null maps, and that's where we get thresholds and determinants to statistical significance. As a minor point, this is sometimes called a permutation test. Actually, you're not permuting anything; you're randomly shuffling things, and it's better described as a Monte Carlo test. Okay, so the kernel, the first one that I'll talk about is the modified ALE, the original ALE method and the modified version. So we start by taking the points, and here I'm illustrating 3 studies, and we have, say, 3 points here, and then this other study only had 2, and this one just had 1. We do have to set the kernel size, so that's a parameter that we have to set. And then we combine these in the usual way of convolution. At first blush, we'll refine that, and you see there's sort of a pile up here. And then you get a map that looks like this. Now, so what is the interpretation? The interpretation in this final, in any one map, is the probability of observing a foci at that location based on a model, an assumption of a Gaussian distribution of the points about some original sort of population point, where our best guess for where that point is the observed location. Then there's the trick of how do we combine foci? Well, so we use the probability addition rule, which is basically for the probability of a union event. So basically, with the final thing we get, this high map here is basically saying what's the chance of one or more foci occurring at this location, and it's done by this rule here. And the same rule is used to combine across studies. And of course, this is conditional on the full tap maximum. So that's one of the problems that Simon and colleagues came to deal with. How do we objectively choose that full tap maximum? And so some of the problems that his revised work addressed was using a mapping, using some empirical data to determine how big should that kernel size be for the given sample size of each study that you're considering. So that's good. That removes this one sort of free parameter and sets it from the sample size. And some other really clever work that showed that you can avoid, in certain situations, you can avoid doing the Monte Carlo test altogether. You can directly work out what the result of the Monte Carlo test would have been, and that allows him to find voxel-wise p-values, avoiding Monte Carlo. However, if you want to do cluster size, you still need to do the Monte Carlo. Okay, and then actually, can I go back one? And just to say that this approach here and the way it's combining is also taking care of, the way this Monte Carlo test is done controls for studies that might dominate one. So if you have one study that just happens to have a whole number of foci, the way this Monte Carlo and its exact computation is done will not let any one study contribute too much. So let's look at the complementary, the similar method, the kernel density analysis method, and its multi-subject version. So here, the math is really the same. We're just taking a different kernel. Instead of a Gaussian kernel, a square or a boxcar kernel, placing one down at each location, and then doing the convolution, which entails adding these things up. So in the original version of this method, the KDA, you simply average these maps, and then you get an interpretation of that this is the average number of foci within a given distance, where that distance is set by the kernel radius. But we have the same problem that studies that happen to report a lot of foci, and this varies a lot between studies and sometimes is influenced by the software, might have an overly great influence on the map. So the revision to this that was suggested in 2008 was a modified version where we just truncate it. So basically, we just sort of say the map per study can never go greater than 1. And this has a nice interpretation now, because this is now, for any one study, this is saying this intensity is there one or more foci within a given radius r? That's the interpretation. If it's 0, the answer is no. If it's 1, the answer is yes. There's one or more within a given radius. And then we get this map at the population level that can be interpreted as what proportion of the studies had one or more foci within a radius r here. And so here this value is 2/3, here it's 1/3, and here, of course, it's 0. So this method also accounts for the structure of the data and for the fact that some studies might have more foci than others by not moving the individual points around, but moving the clusters around in groups, and when it does its Monte Carlo test. And I've just said this statement here. Also, there's a version of this where they weight by the sample size, so it's not as simply the equal weight that I've suggested here. Okay, so those are the main methods you might run across. As you'll hear later, the KDA method is used in neurosynth, while the ALE method is used in ginger ale and other methods. The main limitation here is a struggle for this notion of effect size. Central to any non-imaging meta-analysis is this notion of effect size. If you looked at a meta-analysis of drugs that will reduce the risk of heart disease. There'll always be emphasis on what's the odds ratio. How much has the odds ratio changed when people start taking this drug versus another? What is the effect size? What is the meaningful measure that you can learn about from this group of studies? And we struggle with that. We don't have a necessarily good answer for that in the imaging setting. In the MKDA, we do have an interpretable map where you can say what proportion of all studies had a foci within a radius r. We have some notion of probability, but it's harder to get your head around that in the ALE. And certainly we don't have notions of standard errors or confidence intervals. And this notion of power is also interesting. Simon's actually just finished a paper recently that says that actually you should have at least sort of 10 to 20 studies, I think, but then that's sort of you'll get all the power you need, and it's the influence of other studies that don't coordinate actually may not necessarily reduce your power there. So that's, I think, an issue about the notion of even what a random effect is not well defined in this setting, and it's something that we're still working on. So let me say a little bit more about that. This is a slide I taken from my educational slides for fMRI random effects, where each location, this is not location. Thanks. This is not a location in space. This is actually intensity. This is saying how big is the activation. This subject activated only a little bit with their fMRI signal. Here, this one activated a lot, and here, this one a little. And we'd say, well, it seems like there's evidence that that some of these subjects have activated. But if we actually consider the between subject variation in the bold response, then actually maybe not such strong evidence. And so what we need are methods that are going to actually characterize the spatial spread of variation. And that's something that is still, I'd say, under development. And there's some notion of that in the existing methods, but I think we can do a better job of fully characterizing that spatial uncertainty. Okay, and I'll just skip through this. One thing to worry about is the sensitivity analysis. Something else that is prominent in traditional meta-analysis is looking for evidence of publication bias. And most of these methods, you could really boil down to this following statement. They ask the question, do the effects get worse as the sample size fall? Do the effects get better, basically, as the sample size grows? And in particular, the z-scores, as the sample size gets smaller and smaller in traditional non-imaging meta-analysis, the z-scores should get smaller and smaller. And so you have regression methods and diagnostic plots. You may have heard of forest plots. These are all methods that help us assess, is it the case that as the studies get bigger and bigger, we get nicer effect? Or is it the case that there are small idiosyncratic studies that have a surprisingly large effect that are driving a meta-analysis? And here are some original, here are a couple efforts that were done in this. I don't think these have ever been implemented and integrated into software, but from a paper of Torwegers in 2009, looking at this problem here, where here this looks like a stable effect here because as the effect is getting larger, we're getting roughly the same probability of activation, whereas this is a suspicious point. This is actually showing as the sample size falls, we're getting greater chance of activation, and that's a suspicious finding there because we'd expect the larger studies to be more trustworthy. So this is an area I would say it's currently underdeveloped and we need more work in, but it's something to have at the back of your mind as we try to interrogate the results and see if they're trustworthy. This is one initial go I've made at looking at file drawer bias, was just saying, could we make forest plots? This is one way of summarizing the activation in a meta-analysis focused, a motion meta-analysis focused solely on the amygdala, and we can look at the percent of studies reporting a foci within 10 millimeters of the right amygdala. And these are various ways that we can, this is just the findings from a meta-analysis that came from Torwegers' lab, but I can also, using binomial approximation, get standard errors for these. And you can see that if everyone had used family-wise error thresholds, then all of these are going to be very far away from chance. But if it were the case that all these studies were using a rather uncontrolled 0.01 threshold, actually all these findings are actually not surprising at all. We would expect a bunch of the studies, up to half of them, to have responses if there's no proper control of multiple testing. So these are some things that I think are, again, they're not part of the standard software, but they're things to be thinking about when we judge the results of meta-analyses. And this is actually an outdated slide. We're presenting some more work about this, about estimating the file drawer effect. It can be done. And it looks like from our work that there's something like at least one, for every 10 studies you examine, there's probably at least one study that has not been published, and we were able to infer that based on just the count data that came from the meta-analysis. So I'll stop there, and so just to summarize, I tried to point out the general tools that are developed for non-imaging meta-analysis would directly apply to image-based meta-analysis, but we don't really have much of that data to process, so we focus on the coordinate-based meta-analysis and reviews the two major tools that you find in literature and try to identify some of their limitations. So I'll stop there. Thanks for your attention.
Thanks a lot for the great overview. It's time for one or two questions.
So I was wondering, it's a bit of a flipper question, but is it possible to use some of the methods that you mentioned in these later slides to find brain regions that you'd like to report activations in?
Could we use some of these latest regions to find active? I mean, yes, you can certainly do. I mean, one way of doing a very focused meta-analysis is to just look in one brain region, and that's all I did in that there. I just sort of put a region down in the brain and counted foci. So that's anything that reduces your data down to one yes/no per subject becomes very easy to analyze. That's a good question. Haven't broken that down. We should look at that.
What was the question?
Oh, sorry. The question was that in looking at the publication bias question, and the fact that I said there's something like 1 in 10 studies that are missing, how does that differ with different brain regions? We broke it down by different classes of studies, but you could presumably do the same thing.